Hey guys, welcome back. All right, day 9, electromagnetic radiation. All right, before we dive into this, let's talk about the theme of the book real quick. All right, because we want to talk about when we talk about the theme of the book, why we're going into light. We're doing atoms first. What's going on? Why? Like why? All right. So the theme of the book, right, talks about we want to learn or understand how the structure of the particles that compose matter determine the properties of that matter. All right. Structure determines properties. That's simplified. Structure determines properties. All right. So how it's built matters, right? And we kind of know that. So now we we know the answer to the questions already. Like at this point, right? We're not back in 1800, which we'll start off with in a second. So we kind of know some things. So it has been found or determined right, that electrons so the electrons determine many of the atoms' physical and chemical properties. Right? Why? Because electrons occupy most, and we mean most, we're like almost all, right? Most of the space of the atom. All right. So our goal then, all right, we want to quote unquote understand electrons. That's the goal, right? And it's still, right, we still don't know a lot about them. We're getting better, right? And I don't know how much we'll eventually find out about them, right? We don't know everything there is to know about them, but we're trying to understand electrons to predict behavior, right? We like to predict behavior. So most science, we have an observation. Right? Which leads to a question of why. Which then we can form a test, right? We can test. And then hopefully with that test, there's some results that we can come up with, draw conclusions on, where we end up either to predict or explain. Right? That's the goal. Right? We like to predict behavior all the time. Like for me, if I want a salad, if I want to make my salad taste better, one of my go-tos is adding bacon if we have any that I could do. Right? That's my go-to, right? It makes my salad better. Doesn't necessarily mean it's healthier. I just say it makes it taste better. All right, and so that's just a predicting of behavior, right? And so there's things that we have that predict behavior. sometimes human behavior, but a lot of times we're talking chemical behavior. We're talking things, inanimate objects that do not make decisions. All right. Okay. And so we want to understand the electron as best as possible, where they're at, what they're doing, how they're moving, and figure out with what we know about the electrons to predict behavior of atoms and compounds and molecules and whatnot. So let's talk about the atom, because we kind of know there's atoms, but back in 1800 they didn't necessarily know there's atoms. So there's three schools that were going on, three areas of research that were kind of going on, right? You had the spectra, what's an atomic spectra, right? Well, if I go to day 10 here, I'll show you. These are atomic spectrums, all right? There's the white light spectrum, right? Roy G. Biv, barium's there, helium's there. Those are atomic line spectra, okay? All right, and we'll talk about that was developed in 1900. So this is 100 years after Dalton. Quantum theory started to come along, right? And then atomic structure. So let's talk about atomic structure first. We already talked about Dalton. You know, he talked about atoms, you know, his 5 parts of his atomic theory. Right? Then we started getting symbols and elements, atomic masses. Right? We're starting to understand there's a difference between sodium and potassium and chlorine and all these other, and copper and gold. Faraday came up with the electrical nature of matter. Maxwell, charge on ions. Okay. In 1891, the electron. Now, this is already after Ben Franklin found the kite, and they're using batteries and whatnot. Right? This is already after this, but we didn't know the electron was a unit of charge. 1897, we got the electron in the cathode ray tube by Thomson. We'll talk about that. Millikan did his famous oil drop experiment and got the actual coulombs. So the electron we already defined as having a -1 charge, relatively speaking, compared to the proton. The actual charge in an electron is 1.6 times 10 to the 19th coulombs. Then Rutherford did his gold foil experiment, which is the existence of nuclei. These are all big time, right? And then the atomic spectra, if we come over here to 1860, they found line spectra. And what's weird about line spectra, they're like atomic fingerprints. Hydrogen's line spectra is different than helium. That's different than lithium and sodium, potassium and gold and any other element, right? And they couldn't figure out exactly what was going on. But then Black Body came out, and that's an ultraviolet catastrophe. The book doesn't really go into it. Einstein talked about, he explained the photoelectric effect, which we'll talk about, and specific heat to solid. And then Haas and Bohr came up with the first application of quantum theory, explained the hydrogen spectra, which we'll talk about Bohr. And then we got electron configuration with Pauli, wave properties, and then you have quantum mechanics and wave mechanics and the uncertainty principle, and then bonding theory. And like, if you look at how fast this was going, 1923, you would need a new textbook in 1924, and you would need a new textbook in 1925, and a new textbook in 1926 and 27 and 28. Like, you would need a new textbook every year, and your Chem 1 course would change every year, right? It's not just, oh, there's another edition. There's more stuff. It would be getting bigger every year. This was an explosion here. Big, big names. All right, and that leads us to where we're at now. So now let's talk about light. All right. So the nature of light. Let's talk about some light. Okay. So light, which is electromagnetic radiation, which a lot of times we call it electromagnetic radiation, EM, is a type of energy embodied in oscillating electric and magnetic fields that are perpendicular to each other. Alright. They're perpendicular. Do I have... Yeah, there it is. There's a spectrum. Light is composed of a photon, and it travels at 2.9979 times 10 to the 8th meters per second. A lot of times for 3 sig figs we write 3.00. Okay, and it's made up of a wave, and it has in one direction, let's say the x, well, vertically, let's say it's magnetic, horizontally, let's say it's electric. It doesn't have to be that way. All right, let's talk about a wave. What's a wave? So draw here. Let's do this one. So when you talk about a wave, right, if you graph y equals sine x, it looks something like this, doesn't it? Where we're going to go up, down, right, something like that, right? Keeps going. Well, right here is the same point is right there, right? So that is the length of the up and down. If I did that correctly, hopefully it's right. So that would be the length of the wave. Right, from there to there. That would be the length, or wavelength. And we would write L for the wavelength. And that's an L. It's just Greek. So it's lambda for wavelength. Okay? So that's the length of the wave. Now, the height of the wave, this is the amplitude, and that's the intensity. Okay? That's the vertical height. We care about the frequency, which is the number of times it goes up and down in a second. So the number of cycles right, or wave crest, and we'll use n for that, and that would be the Greek letter nu. All right, and so we know how many, like the frequency, how many times the wave waves in a second. All right, how many times the wave can go up and down in a second. The length is how far they are, and we use c for the speed. Right, because it's constant, and that would equal my wavelength multiplied by the frequency. All right, so the wavelength and the frequency, as one goes up, the other goes down. Okay, now I'm going to go into the photoelectric effect, and then we'll go on from there, because we know, if we go back to light here, right, we know you got Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, right? Those are the, right, and we got wavelengths in meters, so 750 nanometers to about 400 nanometers. Again, some people can see a little, you know, maybe it's not exactly 750 to 400 for everybody. Some people can't quite see down to 400. Some people can, right? So, but that's about the range. Just like hearing, how there's a little bit different. So that's our range, and these are the, all right, wavelengths. So we got like 10 to the 5th meters, 10 to the 3rd meters. So that's a kilometer. You get AM radio, which, believe it or not, is still on. Right? TVA, which I don't think is broadcasted anymore. FM radio, you're in the meter range. Cell phone range, you're here, right? You've got microwaves. Infrared, so notice where the red is. Think of it as infrared, right? Then you got the visible. Violet, you got more than violet or ultraviolet. Then you got X-rays, gamma rays, and it keeps going, right? They keep going. They don't just stop there. Okay, so we kind of know this. Let's go to the photoelectric effect. All right, before we get to the energy part. So here's the photoelectric effect. If you certain lights, all right, okay, if you shine them on metal, electrons will be emitted. So you got a voltage source here, you got a battery, you got electrons going. All right, and what happens is you have light complete the circuit. All right, so this battery is not big enough to make electrons jump, but light will complete the circuit and you get current. And that was weird. And so, of course, Einstein is the one who came up with this. So this is 1905. Einstein. Right, and he talked about the quantization of radiation. So radiation, light, can be considered a beam of particles called quanta by Einstein. His name is capitalized. Right, and renamed photons in 1924 by Lewis, which is a famous name. Right, and so Einstein used this idea to explain the photoelectric effect. All right, so UV light, ultraviolet, causes electrons to be emitted from a metallic surface. All right, so there's two assumptions. One, right? Brighter, or what we're going to call more intense light, so brighter or more intense light should eject more electrons. And two, right, photoelectric effect should occur at any frequency. Right, so here's the thing. Classical physics, which we'll talk about here, classical, right, expects the energy of the electrons to increase upon classical physics expects the energy of the electrons to increase as the intensity of the light increases. which is not so. That's not true. All right, so let's explain. Let's put this into something we do, all right? Because the energy of electrons, right, of the photons, the energy of the photons depend on the frequency of light, not the intensity. So some things some of us do is wash a car. Some of us are very like to wash cars all the time, okay? And we usually do water. If you do it at your house, some of you guys go to the car wash. I mean, it's not necessarily a bad thing, especially if you have to wash your car all year round. Like I know a lot of police officers will just buy their monthly membership to one of those car washes, and they just go through it once or twice a week, and their car's clean. Works out great for them, especially like in the winter months where it might not be so nice to do it at your house. But I have a lot of neighbors, and I've even would do this myself too, where I'd clean the cars all the time at home. All right, so what do you use to clean the car? Well, I could use, I guess I could use a squirt gun to rinse the car off. That would take a lot of effort, wouldn't it? All right, you got squirt guns, you got the water hose, you got a power washer maybe, and let's say you, like I have a fire hydrant right kind of between my house and the neighbor's house. I got a fire hydrant. I could use a fire hose. Now, a lot of us would think that using the squirt gun would be silly. Most of us would use a hose. You could use a power washer with the correct tip, right? The wider, not as intense tip. Okay, you use that like 0-degree tip, it'd probably not be so good. And then fire hose, not a good idea, right? The whole purpose of the fire hose is to go through windows, right? And so the only thing that's changing is the intensity of water with those, right? Squirt gun, not very intense. Hose, more intense. Pressure washer, more intense. Right? Fire hose, even more intense. It's still the same water. It's just the volume of water and the intensity of the water, the speed coming out. Right? And so you would think the brighter you shine that light, you would get electron. Like, that's not how light works. Here's how light works, which is totally crazy. If I had a fire hose and it was red water, right? So the fire hose, if I go down here, and the fire hose of like microwaves or radio waves, huge fire hose hitting the car, nothing would happen. I could blast the car with the red, and it's just bouncing right off, not doing anything. I get a squirt gun, and I squirt one squirt, a little, $2 squirt gun, right? Window's gone. That's how light works. It's totally dependent on the frequency. So the energy is totally dependent on this frequency, not how many there are, which is bizarre, right? Because we're used to having the hose, right? The fire hose is more dangerous than the squirt gun, right? That kind of makes sense. You guys, if you have kids, siblings, right, parents, and you spraying with the hose, right? You have water fights, maybe, right? The hose was always a nice thing. You were limited in your range, but you had a lot of water. Here, right, and because the intensity mattered. Light's not that way. It has everything to do with the wavelength. Just for example, suntans. Most people can absorb some solar radiation and put more pigment in their skin, right, from their starting point. Some people turn into lobsters, but that's a different story. All right. UV light is what gets us to start releasing the pigment from the skin. Infrared doesn't. Right? We feel the infrared from the sun. We don't feel the UV. All right? That's how you can get sunburnt on a cloudy day. All right, so let's talk about how the energy depends on frequency. So the energy, and this is of one photon, is equal to H times nu. All right. So the energy of one photon this is Planck's constant, which is 6.626 times 10 to the negative 34 joules times seconds. And this, of course, is frequency in hertz, or hertz is 1 over second. So 1 over seconds times joules times seconds gives me joules. All right, now, Planck's constant, that's a tiny number. In fact, it equals 0, I'll spell 0, in classical mechanics. All right, so that's how this works. Now, the other formula we had up there is C equals lambda nu. All right, where this is frequency in 1 over seconds. This is speed. Or no, sorry, this is wavelength in meters. And this is the speed in 3.00 times 10 to the 8 meters per second. It's 2.9979 or 78 and some other numbers. There's a lot of numbers to the speed of light in a vacuum. The important point I want to point out, though, is this number and this number are the same. All right? So frequency, wavelength. Wavelength has to do with the color. All right? So I'm going to do something here. I'm going to say that the speed of light divided by the wavelength is the frequency. And since E equals h nu equals hc all over lambda. All right, if I combine these two equations, I substitute in for nu. And so what I want you to look at this is that energy equals constants divided by color. Right? So as the color gets longer, the energy changes, right? So that means each color has a different energy. Each color has a different energy. So violet has a different energy than red. That's what I want to bring up to you, right? So when we look at these equations, not just what the letters are, but what did the letters represent? All right, what did the letters represent? So as my wavelengths get smaller, my energy gets bigger. As my wavelengths get bigger, my energy gets smaller. That's all that means, right? Okay, so this wave, how much energy does this wave have? It has to do with the wavelength. When the wavelengths are really small, a lot of energy. When the wavelengths are really big, not as much energy. Okay, because each color has a different energy, and that's very important. Okay, all right. So now we're going to do, stop here, do some examples.